everybody. We have covered in the previous chapters the fact that the discovery of nuclear fission has been through an application that was destructive. But humanity moved from the energy release from fission into even from fusion. And with the advent of thermonuclear weapons, the energy that was in the range of the kilotons or the thousands of tons of explosive TNT has moved 3 orders of magnitude higher to the level of the megatons, millions of tons of TNT equivalent. And the nuclear processes became, from that perspective, a more like a hurdle that humanity has to overcome, because it can end up civilization and become an extinction event for humanity. So to be able to control it so far in the same way that we are trying to control other filters to our technological civilization. The COVID-19 is one of them. Astral impacts is another one. Global climatic change is another one. You'll find that treaties have been set up to control the spread of nuclear weaponry. So this is what we stopped at last time. And we'd like to cover very quickly the rest of how humanity is dealing with that hurdle of the possibility of nuclear war. So I would like to be able to finish up the chapter on the nuclear world that we are living in today. So we go to our web site and look at our lecture notes where we stopped last time. So we are, interestingly, I have set up already a date for our first midterm, a date for our second midterm, and the date for our final. They will be set up and carried out online on an honor basis. Look at those 3 links here where the tests will be communicated to you. Under the testing stage, I have recorded the meetings, so you can maybe try to access them at the Media Space Illinois. So I'm not sure you can connect to it unless you get permission from the college. So if you go to Media Space, this would be our first lecture recording. So if you miss the Zoom meetings, you can go and check it there. Another interest option here is that the campus doesn't want us to meet on Independence Day. Well, it's not July 4th because that would be Sunday. So the campus is giving you July 5th with no classes. So we'll not be meeting on July the 5th. Let's go to our chapter, complete up the chapter on the nuclear world and look how humanity is dealing with the new hurdle that it has to overcome for our technological civilization to continue. So we go to the bottom of the chapter here. I suggested that now we have weaponry that can reach the megatons of level, millions of tons. One single device can destroy a whole city. The largest device ever exploded is shown here in a replica. It was exploded by the Russians on Siberia. They named it the Tsar Bomba. This is a museum replica, and it would have been able to release 100 megatons of TNT. That's really almost 10,000 times the energy released from the Hiroshima and Nagasaki devices. The scientists at the last moment reduced the fusion part. Notice here, this is the primary, which would be the fission part igniting the fusion part. So they reduced that fusion part here to 1/2, and they ended up getting a release of energy of 56 million tons of TNT to become the largest ever tested weapon in the atmosphere, and that was October 30, 1961. It was 8 meters in length and 2 meters in diameter and about 26 metric tons in weight. It was carried by a Tupolev 95, T-95, or what's called the Bear bomber. And the aircraft is thought to be non-survivable in a real combat sortie because it would be subject to the blast wave and the radiation on the crew of the craft itself. Along the line, you'll find that the United States continued testing because testing in the atmosphere was banned by international treaty. Testing was continued underground for a long period of time. The last test was conducted in 1992. You could see it is cylindrical in shape. So that's a thermonuclear device with a primer maybe in the top here, igniting a thermonuclear device at the end. All nuclear testing has been banned also by humanity. That's a smart move. However, the nuclear power states continue what is called the stewardship kind of program, in which now nuclear weapons are only maintained in a way, or their design improvements are done on supercomputer. You could see here the Sierra IBM supercomputer at the Lawrence Livermore laboratory. Nevertheless, warheads for thermonuclear devices are being miniaturized. This is a W8 warhead, and basically it can generate something in the range of the 100 kilotons. So that's 10 times the yield from the Hiroshima and Nagasaki device. Still, the fear in the development and the existence of nuclear weapons is that nuclear war can start maybe by an accident. And a hero of humanity is Soviet Lieutenant Colonel Stanislav Petrov in 1983. All his instrumentation showed him that it could be a nuclear attack from the United States on Russia, and he had to basically initiate a retaliation, and that could have started nuclear war. But his cool head understood that was a false alarm, and basically he stopped the process in itself. And that was on September 26, 1983. It suggested a single missile followed by several United States missiles has been launched against the Soviet Union. Instead of starting a counterattack process, he called the duty officer at Army headquarters and reported a system malfunction. A later investigation concluded that the Soviet Union satellites at that point had mistakenly identified sunlight reflecting off clouds as the engines of ICBM. So a mistake can start an annihilation process in the whole world. Another false alarm, or as this is more like an accent, happened in the United States with a B-2 bomber, B-52 bomber, as you could see here, getting a malfunction. It crashed. As it crashed, it released 2 thermonuclear weapons shown here. One of them fell by parachute and was basically retrieved, but the second one ended up embedding itself into the ground and is still there in the ground. The Air Force has rented the area around it, and they have some kind of a that was at Goldsboro, North Carolina. They have a fence of the area, and it's too deep in the groundwater. It cannot be extracted, but it is rusting down there. Since then, transport of thermonuclear weapons over the continental United States has been banned. Imagine a 2 megaton, 4 megaton of TNT equivalent thermonuclear device would have exploded near, what's the name of the city? That was Goldsboro, North Carolina in 1961. 3 crewmen died in that instant. We had other false alarm incidents other than the Russian one, but the fear of nuclear war starting is a real extinction event. This shows us when the president of the United States travels, he's followed by what's called the football bag here. It's a bag that contains all the codes that would communicate and start a nuclear war retaliation if it ever hopefully does not happen. This is again another picture of that nuclear football leather suitcase. So the danger is still there, and we are living that danger, and humanity is trying to control it by nuclear treaties and international agreements in general. We are living what is called the nuclear assured destruction, the MAD doctrine, and but there are other doctrines that are advocated by different political factions and different military factions. The nuclear primacy doctrines are sometimes adopted and sometimes dropped. And the United States had a nuclear posture review in 2018. This is the document that describes it. And basically it advocates the renewal of the stockpile of nuclear weapons. These are technological objects, and over time, the radiation emitted and the heat generated affect the efficiency or the availability of those devices. So the United States is embarking on renewing its whole nuclear arsenal. However, we have basically a revived armed race. On March 1st, 2018, 3 years ago, the president of now Russia, not the Soviet Union anymore, and basically made some kind of a presentation, and he presented what you can call a revived arms race that's happening now between the Russians and the United States, primarily because they have the largest number of devices, but all the nuclear other power states are also involved. He presented the new arms race by six new wish lists. And in that case, the Russians are developing an intercontinental ballistic missile. They name it the RS-26. The NATO notation for it is a Sarmat missile, and it has a range of 6,200 miles. So this means that it can go halfway around the globe, and it is some kind of portables. And you could see here mobile devices that roam over the large territory of Russia. This is a depiction of it, the RS-28, and you could see it has emerged devices. This means that it has up to about 12 independent re-entry, multiple re-entry vehicles in general. It has a liquid propellant, and it can go around the defenses, the North American defenses facing the Russia, so it can evade basically radar by coming from the southern hemisphere, where there are no defenses against incoming missiles from the north side. They also, that's related to our nuclear kind of coverage. They have a they claim that they are developing a nuclear-powered cruise missile. They call it the Burevestnik, and a nuclear device powering a a rocket in the Earth's atmosphere, in that case, can have almost an unlimited range, because if you use chemical fuel for a rocket, the range is limited to the amount of chemical fuel that you can carry in the rocket. However, if you use a nuclear reactor, the energy available would be multiple times, so it can loiter for a long time and then hit its target. This is also another cruise missile that the Russians have developed. It's being carried in one case under a MiG a plane, and in another case under a Sukhoi plane. They are trying to attain hypersonic kind of devices by getting the fighter jets to reach supersonic speed and then releasing what they claim is a hypersonic device using a ramjet rather than just a normal jet. So this is a depiction of the MiG-31 supersonic interceptor, and possibly, we all know it's in the development stage, the M10 2,000 kilometers air launch cruise missile. They call it the Kinzhal. Kinzhal stands for dagger, this would be the cruise missile that would evade the radar systems on naval vessels in the oceans of the world, because it would hug the ground and would have a nuclear reactor apparently powering it. They show here experiments with that on that type of a cruise missile. You notice it has some kind of wings deployed here to control its flight. So now that is a new development in the sense that they're trying to use a scramjet. Ramjets, of course, are a new type of an engine compared to a conventional ram engine, but then you heat up the air as it comes in from the front. And if you use combustion, it's designated as a scramjet. It can reach speeds between Mach 5 and Mach 15. Mach is the speed of sound, so 15 times the speed of sound. Remember, we calculated in the last lecture the speed that ICBMs reach in the range of 23 Mach. However, these ramjets can reach a speed of the 15. So this is still hypersonic, and it's not pie in the sky. You could see it here hanging at the bottom of, I think, a MiG-31 airplane. So that's the what they call the Dagger air-launched cruise missile. They also have a third type of wish list, and this would be glider weapons. So in that case, the device is launched into space and then allowed to come down from space, surrounded by a plasma sheath. So if you surrounded by plasma sheath, maybe some exhaust from the rocket engine in the back of it, you will create stealth. The speed itself, 15 Mach 15 times the speed of sound, or 23 times the Mach 23, the speed of sound, is already a stealth feature. It will come at you without any kind of advance warning. They don't need even to equip those glider type of devices with any kind of explosive weapons. Just the kinetic energy of them hitting a target can lead to a huge release of kinetic energy. And they suggest that this is one of them under construction. They call it the booster glide. They call it the avant-garde kind of a device. So the aeroballistic Kinzhal dagger, that's this is another, the number 3 wish list of President Putin in that case. This is the hypersonic dodging boost glide cruise missile. They call it avant-garde, and it has to do with fencing. They say en garde to the opponent. Then they have another nuclear system that's why we are covering it. It's of interest to us. It's nuclear. It's a nuclear drone submarine. So that would be an underwater powered submarine with a nuclear reactor. And this was a dream of the Russians for a while. Russian academician Sakharov, at one point, he's helped the development of nuclear weaponry in Russia or the old Soviet Union. He said, after testing the big quote unquote product, I was worried that for him, there is no good carrier. Bombers do not count, they are easily knocked down. That is, in a military sense, our work was wasted. I decided that such a carrier could be a large torpedo launch from a submarine. I imagined that it would be possible to develop a straight flow water system atomic jet engine for such a torpedo. The purpose of the attack from a distance of several hundred kilometers would be the enemy's port. So in that case, I would explode a 100 megaton device. The explosion would generate a tidal wave, like what happened at Fukushima, and it can destroy whole cities, coastal cities or shore cities, San Diego, New York, and so on. The body of such a torpedo can be made very durable. It can sit silent at the bottom of the ocean and initiated to attack the other side in general. So here they show some depictions of that drone, nuclear submarine, drone in the sense that it doesn't have humans manning it, and they suggest that this is one of these submarines under construction. And they use a nuclear reactor, so it can basically remain submerged for a very long time. This is designated now as UUV for unmanned underwater vehicle. Another item on the wish, oh, this is an interesting aspect of it. This is a description of such a submarine, either that it carries a torpedo under it, and you notice here, this is a reactor for, in Russian, it goes to a turbine here to run the propeller. So they have two versions of it, either in the form of a torpedo or in the form of a whole submarine. And the torpedo version is called the Canyon Status 6 compared to an ICBM. You could see it is much larger than an intercontinental ballistic missile, and it's much larger than a conventional torpedo. This one would be 7 meters in length, an ICBM 12 meters in length. That Canyon torpedo would be 24 meters in length. And these are descriptions that were published by the Russians of that torpedo. And in fact, it seems that they have it really being developed. You could see here they have faded out the shape of the propellers, because the shape of the propellers is a military secret. And they suggest that there would be the torpedo shown here to be launch an attack about coastal cities where there are military bases in general. They call it an ocean multipurpose system status 6. And then they have the third item on the wish list of President Putin is what they call the Peresvet mobile laser. As you could see here, the United States has also developed lasers, but they are being deployed on naval vessels, on ships, whereas the Russians have them on mobile land-based systems. They can go over the large expanse on rails. I think they are on wheels over the large expanse of Russia in general. What do we do about this as humanity in general? The main effort goes through what's called the NPT. I would like you to remember those acronyms so that you can read about them in the literature and understand what they mean. Is a non-proliferation treaty. The non-proliferation treaty is a treaty signed by most of the nations of the world. And in that treaty, the nuclear power states commit themselves to the elimination of nuclear weapons, which obviously hasn't happened. But in return for the other signatories to the treaty, the NPT, the nations that signed it receive, in principle at least, help from the nuclear power states in developing peaceful nuclear energy, peaceful nuclear energy. And it is managed by an international organization, the International Atomic Energy Agency. That's the acronym for it is IAEA. This was followed by another effort that is very recent, the international campaign to abolish nuclear weapons. It's designated as ICAN. And the treaty did not come into force until 50 nations would sign it. And that happened. Honduras was the 50th country. The accord was approved by 122 countries at the United Nations General Assembly in 2017 and needed to be ratified only when 50 nations would have signed it. That happened by Honduras lately in general. So that is another way that humanity is fighting the possibility of its extinction. Efforts at controlling the proliferation of nuclear weapons are nowadays centered on the Non-Proliferation Treaty. 133 nations have signed it in 1968. Some states, including India, Pakistan, China, and Israel, advanced diverse reasons and excuses and have not yet signed nor ratified the treaty. North Korea withdrew from the treaty and is negotiating rejoining it for economic and security incentives. This is a show of force of the SS-25. That's an ICBM, a mobile kind of system shown. Basically, it's also used in silos. Land-based Russian ICBM paraded on Red Square in Moscow. So that's part of the nuclear wars. This is the Russian device there. You could see its size. It's just huge in size. It's kept in silos underground like the United States. We have the Minuteman device. Not only Russia is into the arms race, but China is showing here their ICBMs on parade in 2009. And this is a Chinese ICBM. Look at the size of it compared to the size of that gentleman here and another gentleman here and there. These are all underground. So the arms race is not just between Russia and the United States, but also other countries have joined the process. This is now a NATO kind or American nuclear ICBMs based in Germany. It's sometimes puzzling to see how these ideas of destroying each other or the mad concept, mutual assured destruction, is happening. This is some material from a Chinese newspaper where they suggest the fallout from the bombing of West Coast cities in the United States here. And you'll find interesting enough that they also target all those dots here are cities that they're targeting. Basically, so on the West Coast, they target Seattle, Los Angeles, San Francisco, and San Diego. But they also counter what the arms control people call counter value targets. And they include Green Bay, Wisconsin. I don't know what's in Green Bay, Wisconsin, other than the Packers football team that needs to be attacked. They also target here Lansing in Michigan, Albany in New York, Manchester, New Hampshire, and Augusta, Maine. And that's basically published in the Global Times newspaper. It's an agency in China. China apparently also built a Great Wall underground. So it's a set of tunnels shown here underground It stretches over 5,000 kilometers in the Hebel region, and it is reported to harbor a counterforce of 500 ICBMs in around 100 silos. So that's underground, it cannot be seen. Of course, the United States had that same kind of, not underground of system, but underwater in nuclear submarines. The Russians have their own missile silos. That was one in Kazakhstan. I wonder whether it still exists in Kazakhstan in 2007. And of course, there are bombers, a Tupolev 160 Blackjack bomber. It is being shadowed by an F-3 Tornado jet in the UK. The missile silos are spread not just in the United States, but also over Europe. This is 20 of those missile silos. You could see they have big lids on them. They would be moved to the side here on rails, and the silo would be, and the missile would be fired from there. So these are part of the NATO's counterforce against the Russian. You could see here the lid on the top, which can take a nuclear attack, but moved on rails. Rantoul here in the United States used to be a training site. I think they have a museum now that at some point people would visit those, the silo that was used in the training when they had open houses. The main force of the United States is centered on the new devices, the B-61 thermonuclear free-fall precision guided munitions. I have tail flaps, and the whole arsenal of the United States is being renovated along this line. Not only that, but of course we have now fighter jets that are stealth, meaning that the fuel tanks as well as the weaponry is kept inside the body of the jet, so as to minimize the radar kind of signature of it. That's F-35. It carries that thermonuclear type of a device, the famous now B-61. The fins here in the back tells you that basically they can be directed towards their targets, and that gives you an idea of the size of it compared to the gentleman standing right next to it. The development of this weaponry involves really many different organizations and companies and manufacturing process, and but they can be carried on a large range of aircraft like F-15, F-16, and they can reach a speed, not the Mach 23 of the ICBMs, but maybe supersonic Mach 2 speed, the 2 times the speed of sound. So this is testing or training on a Mach B-61 launch device. And this is an F-15 fighter dropping a GBU-28. That's an Earth-penetrating 2,300 kilogram munitions. It penetrates the Earth to hit fortifications and armaments kind of silos in general. In essence, then you'll find that the United States and Russian missiles and bomber arsenals, according to the Federation of American Scientists, you find that the United States has 400 intercontinental ICBMs, basically the Russian Federation's 300, submarine launched ballistic missile 240, the Russians 160, and the United States uses 60 bombers, and the Russians have 55 in the arsenal. So the dependence is primarily on either submarine launched missiles, ICBMs, or land-based in silos in general. This is a new type of trench warfare, basically was used in the United States to desensitize army personnel against nuclear explosion. So they have a nuclear explosion here and the personnel hiding in a trench. So that's a new kind of trench warfare where it's not like the First World War, where poisonous gases, toxic gases were used like chlorine, but nuclear weapons would be used, and that is a test using a 43 kiloton TNT equivalent in 1953. Those people were exposed unnecessarily to radiation. Now we are living in a world where it is not the 43 kiloton or the 10 to 15 kilotons of Hiroshima and Nagasaki, but we are talking about almost standard size for thermonuclear weapons of 10 megatons. This is the Ivy Mike test. It's expanded the mushroom to a range of 100 miles at the edge of the stratosphere at a height of 25 miles. Such a device would cover a whole city, like the city of New York here, by just a huge fireball. So these are not meant to destroy just troop concentrations in warfare. These are meant to destroy whole cities. So this is targeted against civilians, which does not adhere to the Geneva Convention. And one very fearful application of the MAD doctrine is the concept of the electromagnetic pulse, EMP. Remember that acronym again. This is a test of a device in the upper atmosphere generating an EMP, or electromagnetic pulse, out of a 1.4 megaton of TNT equivalent. That was called the starfish event. Basically, it affected the Van Allen radiation belts around the Earth. It generated an aurora borealis over the cities in Hawaii in general, over the whole Hawaiian Islands. And it can destroy all the electronics if it is exploded on top of a city. So there was a fear with the rise of the tensions between the United States and North Korea that they could use such a device against the United States. And their ICBMs could reach Hawaii. And on January the 13th, 2018, only 3 years ago, there was a false alarm over Hawaii. And in that case, the mistake was that they were running a software that was supposed to be a test. And somehow somebody made a mistake and ran it as if it was a real alarm. And the police and the announcement in the streets caused a huge panic. And the frightening part of it is that father here trying to convince his reluctant daughter to go hide in a basically in a manhole in the street to protect her, apparently from what people were brainwashed into thinking that it was an EMP attack by North Korea. And look at what kind of destruction North Korea would have been subject to based on basically a false nuclear alarm in general. In the United States, there is a plan called the SIOP, Single Integrated Operational Plan, that was initially suggested by General Curtis LeMay. And he was he had the idea of use strategic bombers to drop about 400 nuclear devices on most war-to-pact cities, over 40,000 in population around 1947. In 1960, the United States formulated nuclear war plans, what's called that SIOP. It envisioned a massive simultaneous nuclear strike against USSR nuclear forces, military targets. According to some USA estimates, the attack would have resulted in the deaths of 285 to 420 million people. I'll let you judge what kind of thinking those people were thinking. The United States withdrew from the INF treaty in it was signed in 1960, and the INF is was signed initially as a way of controlling nuclear weapons in Europe, and in October 2018, President Donald Trump suggested pulling the United States out of that INF, which stands for Intermediate Range Nuclear Forces Treaty. The Russians had accused of the United States of not adhering to the treaty, and the United States reciprocated with the same problem. And basically, the United States withdrew from it, and the issue was that Russian SSE-8 Novator, a cruise missile that was not allowed as part of the treaty according to the United States. There have been lots of treaty violations on low yield testing. Some countries have been testing low yield devices without categorizing them as nuclear devices. And quote here, on that type of testing, the United States believes that Russia probably is not adhering to its nuclear testing moratorium in a matter consistent with the zero yield standard. So there are some violation of the treaties and disguised under one form or the other. Accordingly, there is a group of scientists and people in Madison, Wisconsin, that publish the Bulletin of Atomic Scientists, and they developed what they call a Doomsday Clock. And the Doomsday Clock suggests how humanity can be extinct by a nuclear war. They suggest that we were 17 minutes before midnight. Here, midnight is shown here on the clock, when the Soviet Union exploded their first nuclear test. In 2015, we were about, let's see here, 2015, 1981, 2015 would be right here, probably. The climatic change and nuclear concerns were a main concern. And then comes the latest clock shown here. That was on January the 25th, 2018. And then to January 23rd, 2020, minutes to midnight, we were only 3 minutes or under to midnight. And that was in 2020, only a year ago. The concern is climatic change and nuclear concerns, climate, nuclear, and cyber warfare. You could see some entities in Russia lately have targeted for ransom oil facilities and oil pipelines in the United States. So we are living a really dangerous world from the perspective of nuclear events in general. This graph here shows us the nuclear testing all over the globe since 1943. Notice those tests in the Sahara Desert by the French. There were tests in the ocean, and there were even tests on the Asian continent by the Russians. So testing luckily has been banned today. In 2017, July, 100 countries endorsed the United States treaty to ban nuclear weapons altogether. So humanity has some smart people who understand the extinction kind of threat of nuclear war. And that was through the campaign to abolish nuclear weapons. Basically, that organization behind the treaty, the international treaty, was awarded in 2017 the Nobel Peace Prize. And once Honduras, as I mentioned earlier, became the 50th country, the treaty came into basically into effect. So that is the hope of the world, not just the NPT or the Nuclear Non-Proliferation Treaty, but the treaty to totally abolish nuclear weapons. I can campaign to abolish nuclear weapons. So this is the hope of the world, so that it doesn't become an extinction event or a filter, according to cosmologists, that could lead to the end of our civilization. There is also another treaty, the 1967 Outer Space Treaty, contains no language that specifically prohibits militarizing space, except when it comes to weapons of mass destruction, like nuclear weapons. It is required that all states' use of the moon and other celestial bodies is for peaceful purposes. Exploring and using outer space must be done for the benefit of all countries, and all exploration and use must follow international law like the United Nations Charter per the treaty in general. I'll let you read more about it, but the interesting thing that I can end up this is science fiction. I think I can connect to the YouTube ending of the 1983 movie, War Games. Let's see if we can get to it. And it gives us a nice way of ending the chapter. That's 5 minutes of watching.
Put the list back up?
No, we already tried that.
Put it up.
Yes, put it up.
You are invited to watch that movie, obviously. Rent it.
It's not on the list.
It's not on the list. Go ahead. It's got to be in there somewhere. You're in. Order, get this on the missiles.
No, no.
It's a tic-tac-toe game that the computer is playing with its owner.
5 numbers. It's got half the code.
And
Put X in the center square. Yeah.
Six up.
There's no way you can win that game.
I know that. It doesn't. It hasn't learned. Is Earl going to make it play itself?
Yes, number player 0.
if you haven't watched that movie, that clip here can invite you to find a way of watching it on YouTube.
Learn, goddammit.
Must be caught in the loop, storing more and more power from the rest of the system.
9 numbers. 10. It's got the code. It's going to launch.
Colonel Conley Colsack, give me a launch status report. Major Davis, get me the president. Yes, sir. How you doing, Colonel?
Sir, all landlines out of the mountain are dead. I'm trying to break through on satellites.
Okay. It's learning. sure?
Strange game. The only winning move is not to play. How about a nice game of...
So this is the whole moral of the movie Simulation, is that in a nuclear exchange, nobody is a winner. And the best strategy is not to play the game. And I invite you to watch the whole movie at some other time. I'll stop here in between chapters and invite you maybe to the chat room if you have any questions. I created a group me for the course if anyone is interested in joining. This is a message from Francesco Camp. All right, I don't mind your building a group me, except that you commit yourself when you take the tests to be an individual effort, not a group effort, please. Any other questions? Okay, I'll go back now. We are ready that so far, after we covered the chapters on the history of nuclear energy, the world that we are living in terms of the possible peaceful applications of nuclear energy, but also the possibility of its becoming an extinction event or one of the filters that could end up our technological civilization. It's as important for the future of humanity as much. I think I want to end this thing, but it won't let me get out of it. All right. Now, what I want to do is go back to our lecture notes. And we did mention in the previous chapters the possibility of producing plutonium-239 from uranium-238. We also mentioned the fusion reaction that can happen in thermonuclear devices. In our future, we'd like to develop thermonuclear energy in a peaceful way. So we have to go and deal in a more quantitative way with the processes that govern the nuclear age. In our class, our ambition is to cover 3 of the 4 forces of nature. The postulate that we have about the start of the universe, 13.7 billion years ago, is that a Big Bang occurred. And at the time of the Big Bang, the cosmologists postulate that the 4 forces of nature, they're talking about the 5th force, by the way, lately, but the 4 forces of nature were combined and they separated at that point. And the 4 forces of nature, as you know, are first the nuclear force. And this is the one that is described in fission and fusion processes, for instance. We have also the weak force that is more or less described in radioactivity. Then the third force is the electromagnetic force described in electromagnetic radiation, which is light. Our interest is going to concentrate on high energy radiation. In that case, it would be X-rays in the energy range of the kilo electron volts, as well as gamma rays, which have an energy range in the million electron volt. And the fourth force of nature is obviously the gravitational force. And we leave this for all the other classes that you are covering in engineering and science and physics and so on. So we'll cover the radioactivity part later on, but we really have to start with dealing with a strong force, the nuclear processes, and cover material that maybe you haven't covered in other courses in high school. So the nuclear processes, fission and fusion, are described by the strong force. And as you know already, the strong force is based on nuclear reactions, reactions between the nuclei rather than between the atoms of different elements. So if we talk about the chemical reactions, for instance, if we burn coal in fire, the carbon interacts with oxygen in the air and generates carbon dioxide. We all know that. Now, if you have hydrogen, hydrogen also can interact, in fact, violently with oxygen in the air, and you get, 2H2, water. In a nuclear processes, we are processing uranium with hydrofluoric acid. You'll find that in that case, you reduce that uranium into uranium tetrafluoride for use maybe in the Calitron electromagnetic separation process that we'll cover later, and you also produce water. Typical of chemical reactions, as we have learned so far in all our classes in chemistry, is that the energy release is in the electron volt range. In fact, the ionization energy of the hydrogen atom, ionization means that you strip the electron out of the hydrogen atom, is 13.6 electron volts. So remember this, it is electron volt. So that's the one of the first features of it. Energy is released, that's fire here. Carbon being burned into carbon dioxide. In chemical reactions, as you could see, the reactants lead to products, but the identity of the elements in the reactants, like carbon, is maintained. The carbon on the left-hand side reappears as carbon in a different chemical form on the right-hand side. The oxygen is still oxygen on the left-hand side, reappears as oxygen in the right-hand side. Now, this is very different than when we have reactions between the nuclei themselves. You'll find that we get basically transmutations. And that was the dream of the alchemists, turning, say, the transition elements like copper or mercury into gold. However, this happens in modern days in nuclear reactors and particle accelerators, and in the past in nuclear explosions. For instance, in nuclear reactions, we would interact helium for the nucleus of helium-4 with the nucleus of aluminum-27. So if you bombard the foil of aluminum with alpha particles from the source of radiation, you find that the nature of the reactants differs. You find that you end up with silicon instead of the aluminum, and the hydrogen atoms are released. So you'll find that the reactions here occur between the different isotopes of the elements, and the isotopes in general take that form Z1, which is the charge, or the what we call the atomic number, the number of electrons surrounding the aluminum nucleus. And of course, because the atoms are neutral, an atom of aluminum-27 would have 13 electrons as well as 13 protons in the nucleus. Now, if you have 13 protons in the nucleus and 13 electrons, the isotope aluminum-27 has also 27 minus 13, 14 neutrons or elementary particles that have a neutral charge. They don't have a charge, negative or positive. So in general, we represent the isotopes or nuclei in general as some X. It could be aluminum, or nitrogen, helium, with an atomic number Z1, and what we call the mass number on the top, Z1, the atomic number is the number of electrons or protons, and A1 would be the total number of nucleons in the nucleus. So we have here 27 neutrons plus protons. Notice here that the reactions occurs with a variation between the reactants and products in terms of their chemical composition. This was aluminum and helium-4. Now we have silicon and hydrogen. Also, an alpha particle can interact with nitrogen in the air. Remember, air we breathe is 70% nitrogen and maybe 15% oxygen and some other gases like CO2, neon, and so on. And in that case, you find that the nitrogen turns into oxygen, and the helium-4 results in the production of hydrogen in that case. In chemical reactions, as well as nuclear reactions, like we are showing here, we end up with a difference in the masses between the reactants and the products. And that difference in mass exhibits itself in kinetic energy of the products that come out from the reaction. So initially, that silicon-30 and that hydrogen nuclei come in apart after those two, the alpha particle and the aluminum-27 combined together. They come apart with a large charge. The electrostatic charge repels the two nuclei from each other, and that kinetic energy that they carry would have been a change in the mass between those reactants and the product. And in nuclear fission and fusion, you'll find that that delta M here, according to Einstein equation, becomes the kinetic energy of the products, or the kinetic energy of the reactants, as we'll see in a moment in general. All right, now in all processes in nature, nature likes balance. It doesn't like instability. You'll find that when those nuclear reactions happen, there is a conservation of two important quantities. First, you conserve the charge. So when you get that reaction here between two elements, two isotopes with charge Z1 and charge Z2, you'll find that Z1 plus Z2 should be equal to Z3 plus Z4. So charge has to be conserved. In addition, the total number of nucleons has to be conserved. So you'll find that the 27 plus the 4, A1 plus A2, should be equal to A3 plus A4. So here we have two conservation relations in nuclear reactions. The conservation of charge, Z1 plus Z2 is equal to Z3 plus Z4, and the conservation of nucleons, the total number of protons plus neutrons in the reactants should be equal to the total number of in the products. And those two conservation relations help us determine, if I know what are the two reactants in a given reaction occurring, I can tell what, by balancing the charge and balancing the nucleons, I can determine what are the products of the reaction. For instance, if I know that by having helium bombard a foil of aluminum, that I can see hydrogen being released, I can balance the equation. 13 plus 2 is 15, and the hydrogen would have a charge of 1. So I must have 14 here in that other product. This is called the binary reactions, because two reactants produce two products. And 14 in the periodic table of the elements is the charge of the element silicon. So it becomes silicon. And I can also tell which isotope of silicon it is, because 27 plus 4 is 31, and the hydrogen has a mass number of 1. So 31 minus 1 will tell me that this is the isotope of silicon that contains 30 nucleons. So by balancing the charge and the total number of nucleons, we can basically balance nuclear reactions that are, of course, reactions between the nuclei, not between the atoms. A third conservation relation has to also occur. And that third conservation relation is the conservation of mass. Mass is not going to disappear in nuclear reaction. So that delta M in the reaction that we wrote earlier should be equal to the mass of the reactants minus the mass of the products. Obviously, that mass is converted, as we suggested, to kinetic energy of the product. So if we know what are the reactants, what are the products, and we know the masses of all of them, they are measured by mass spectrographs, I can determine what is the change in the mass, and then we'll proceed further and use Einstein equation. And by using Einstein equation, we can tell how much energy is released. So the conservation of mass is also what we can call conservation of energy. Nature's likes doesn't waste anything. Things, energy is conserved, as we could see. The charge is conserved in the reaction. The total number of nucleons is conserved, and well, the mass, energy, mass or energy is also conserved. So as we talk about the mass conservation of nuclear reactions, we would like to translate that difference in mass into a difference in the energy release, or the energies that we have to provide the reactants with for that nuclear reaction between the nuclei to proceed. Now, we need to have data, and the chart of the nuclides presents us with this data. We need to know the masses of that helium-4 and the aluminum, the mass of the nitrogen-14. So we can go and if we know the masses, we can determine the energy release. The masses in the chart of the nuclides, of the table of the nuclides, as you have already worked on probably in the assignment that I gave you earlier, is describes in atomic mass units, and AMU. In the old literature, if you go to the library and look at very, very old reports or books, you'll find that the standard that was used was the oxygen 16 isotope of oxygen. In the modern literature, the choice has been changed from oxygen 16 to carbon 12. This is the most abundant isotope of carbon. So when we take the isotope of carbon, why? Because in organic chemistry describes life on Earth, and carbon is part of most living creatures on Earth. So if you take the 1/12, the mass of carbon 12, this is by definition the atomic mass unit. So the mass of the carbon 12 now, 12 multiplied into 1 here, is 12 atomic mass units. So if you go to the chart of the nuclides and you look for the mass of carbon 12, you read exactly 12. So it is used as some kind of a standard of a scale, like the meter in the Bureau of Standards in Paris, France. It's just a length of platinum that we call the meter. Here, the mass of the carbon 12, we designate it as 12 atomic mass units. On that basis of the atomic mass units, if you go back to the nuclear reactions that we wrote earlier, you'll find that we can get an exact value for that 27, the total, the mass number. In fact, because the 13 protons and the 14 neutrons do not have an exact rounded number. So it's the 27, or the mass number, is a rounding. It's a total number of nucleons because each one of them has about a mass of 1 atomic mass unit. But if you go to the chart of the nuclides, a more exact number for the mass of aluminum 27 is 26.981541. The mass of the helium atom in that case, because those masses really are shown for both the nucleus and the electrons around it, because that's what the mass spectrograph measures for us. The mass of the silicon-30 is in fact 29.973. The mass of the hydrogen ion is 1.007, and the mass of nitrogen-14 is 14. So if we know those masses, and we can basically determine what is that delta M, the difference in mass that happens in those reactions. So let's take an example of the first reactions. What is the difference in mass between the reactants and the products? It's a mass of the aluminum 27 plus the helium nucleus plus minus the mass of the silicon 30 minus the mass of the hydrogen. And when we add those two masses and of the reactants minus the two masses of the products, we get a positive number, 0.002554 atomic mass units. And you understand now why is it that we took 6 decimal points here, because the difference really is at the 3rd decimal point. If you just go and get right to 26.98, you lose resolution. That's why we take the masses with maybe 5 or 6 decimal point after the period right there. If we consider the other reaction between helium-4 and nitrogen, you'll find that the mass of the nitrogen in atomic mass units is 14.003074. The mass of the alpha particle is 4.002 minus the mass of the products, the hydrogen nucleus plus oxygen 16. And lo and behold, it's 18.00, and we get a negative number in atomic mass units. And that is the energy, the mass difference between the reactants and the products in those two reactions. Oh, wonderful. When the mass is positive, that means that there is a release of energy. Energy is released because here that mass of the reactants being larger than the mass of the product means that that mass is has been turned into energy. In that case, in nuclear and radiochemistry, which we are really doing right here, that's what it is, we call this an exothermic reaction, meaning that that reaction releases energy, and we call this an exothermic reaction. On the other hand, for the reaction between the alpha particle and nitrogen-14, the energy is negative. This means that if you want that reaction to proceed from the left to the right, we have to provide energy to that alpha particle. We have to accelerate it maybe in a particle accelerator by this amount of mass so that the reaction proceeds from left to right. Now, this is very interesting here because in the literature of nuclear and radiochemistry, from which we are adopting that material, the terminology is the exact opposite than what we get in conventional chemistry. So the exothermic in conventional chemistry is called endothermic, and the endothermic in radiochemistry, this is chemistry of radiation and nuclear reactions, it would be named the exact opposite. So because we have quite a few chemical engineers in our class, I am going to highlight this sentence here. Notice that this terminology is the opposite of the ones used in chemical reactions. We are not making conventional chemistry here. We are making nuclear and radiochemistry. All right, so in those nuclear reactions that we have listed before, in the balance of the mass, we have a balance of mass now, wonderful, but we want to balance it also in terms of energy. We can determine the delta M by subtracting the masses from the reactants and the product. Can we turn that delta M into energy release? This is of interest to us, not just the mass in that case. So in that case, we are going to imply the Einstein equation that suggests that mass and energy are different forms of the same nature. In that case, mass and energy can be converted one into another. And I'll show you how it can happen actually and observed in the laboratory. All right, to be able to turn that mass into energy, we are going to involve a law from physical chemistry, which is called Avogadro's law. All of you have been basically exposed to what is Avogadro's law before, but let me remind you what it is. This is one of the important laws in the field of chemistry. It states that the number of atoms or molecules in a mole of any substance is a constant. And that constant is called Avogadro's number. It's 0.6, 10 to the 24th, very large number. We cannot even weigh it or count it, but we can deal with it through our intellect, atoms per mole. What is that mole? The mole is an abbreviation for 1 gram molecular weight. So 1 gram molecular weight is just named a mole. And how do we determine what is the gram molecular weight of the mole? It is the amount of the substance having a mass in grams. Remember, we are using here the CGS system of units, so centimeter, gram, second, and the amount of a substance equal to the atomic or molecular weight of the substance, obviously in atomic mass units. So if you have a carbon 12 gram of carbon 12, it would be 12 divided into the the atomic, approximately the atomic mass 12. So that's 1 mole of 6 carbon 12. If you have 48 grams of carbon 12, the 1 mole is 48 grams divided into the atomic weight of carbon 12, which is approximately 12. It's 12 point something, but I'm showing it here as 12. So that would be about 4 moles of carbon 12. So if you want now if you have 48 grams of carbon 12 and you have 4 moles, you take the 4 moles, multiply it by Avogadro's number, and you get in that case a total number of atoms or molecules or nuclei, depending on the context, that 48 grams have. What is the number of moles then? It's the mass of the element that we have at hand divided by the atomic or molecular weight. I'm writing it here as A, as an abbreviation. For instance, again, if you take 64 grams of oxygen, oxygen has 2 atoms of oxygen 16. So 64 divided by 32, that would be about 2 moles of the oxygen gas in that case. I'm putting here an approximate sign because this 16 here is an approximation of 16, maybe 15.999 or something. So just to demonstrate the issue, and it will not be very different from the actual numbers. Since 1 gram of mole of contains Avogadro's number in atoms or molecules, and 1 gram of mole of carbon 12 has a mass of 12 grams, you'll find that the mass of 1 atom of carbon 12 is the 12 divided into Avogadro's number. We go back to Avogadro's law, and in that case, if I divide here by Avogadro's number, you'll find that we can calculate the mass of 1 atom of carbon 12. It is 1.99 10 to the minus 23 grams. There is no scale that can measure this. Oh, but we are, as humans, smart enough to use mathematics. We can infer it from the math that we are doing right now. And basically, this helps us establish the mass of that atomic mass units in grams for a reason that will become later known. You take then 1 atomic mass unit of carbon 12 is that 1.99 10 to minus 23 divided by or divided into 12. So 1 atomic mass unit then, according to our definition of the mass of carbon 12 as 1 atomic mass units in what is 1.66 10 to the minus 24 grams. Now, Avogadro's law tells me that 1 gram molecular weight or 1 mole of any substance contains Avogadro's number in atoms or molecules or nuclei. So suppose that you have G grams of any substance. If you divide it by the molecular weight in atomic mass units, multiplied into Avogadro's number, you get the number of atoms that mass G of the substance. And this is really Avogadro's law. Now, if you use actual mass in grams here, you get the number of atoms. However, you'll find that in some applications that we are going to deal with, we are not really interested in the total number of atoms. We are interested in the density of the atoms or the nuclei. In other words, how many nuclei I have per centimeter cubed, rather than I am interested in the total number of atoms or molecules or nuclei. So in that case, we divide that mass G into the volume, and if we divide the mass into a volume, you get a density. So if you take the density of any substance, water is 1 by definition, gram per centimeter cube, or you take the density of uranium, 18.9 grams per centimeter cube, divided into the molecular weight, you get the number of gram moles or gram molecular weight, you multiply it by Avogadro's number. So if you use the density instead of the actual mass, you get a modified form of Avogadro's law that we are going to use extensively later in the semester. So we'll designate this as N prime, or the modified form of Avogadro's law. And having defined Avogadro's law now, we can create an equivalence between the mass and energy. And you'll find that it will become simpler as we proceed further, so don't get discouraged. We invoke, in that case, a relationship between mass and energy. That is a very famous Einstein equation. Now, if you use the mass here in grams in the CGS system of units, and we describe the speed of light, c, in centimeter per second, the energy release is going to be in the units of energy in the conventional system of units, or the CGS, centimeter, gram, second, in terms of the units of energy is the erg, ERG, and the plural is ergs. An interesting situation occurs here before we move further, is that energy can basically be a transformation of mass into energy. But if you have electromagnetic radiation and electromagnetism, you do not describe the energy of a photon in terms of its mass. Oh, it doesn't have any mass. So we describe it in terms of what the frequency of the radiation. Nu here, this is the Greek alphabet N, nu, is equal to 1 over the wavelengths of the radiation multiplied into the speed of light. And then this h here is a constant of nature that we call the Planck's constant. It has units of erg multiplied into second, 6.6 10 to the minus 27. So these two equations here, 13 and 13 prime, are very interesting because one of them establishes mass as being convertible into energy, and the electromagnetic radiation also is convertible into energy. All right, so in that case, either mass is equivalent to energies because they can be transformed into each other, or electromagnetic radiation already carries energy in general. So here we are going to venture in our class that's not in the other textbooks that you'll find in any library, and equate the two to each other. So if I have a mass, it contains energy. If I have electromagnetic radiation, it also contains energy. So if we equate that mc squared to h nu, we get h divided into c over lambda, which is the same when you take the frequency as being 1 over the wavelengths multiplied into the speed of light. And in that case, we will unify mass. Mass can be either in the form can be in the form of radiation. So if you just eliminate E between the two equations, you'll find that M is equal to Planck's constant divided into C squared, the frequency of the radiation, or 1 over the wavelengths multiplied here into C, and the Planck's constant appears as a proportionality constant. And that is something that you observe in the lab. In fact, this is an experiment in what is called a cloud chamber. So what is a cloud chamber? On engineering open house, students in the physics department like to show an experiment where they get a saturated vapor of a liquid, alcohol, in a sheet of basically sheet of paper. In fact, they place on top of it a glass cylinder, a cylinder that has a top as glass, and they place it on top of a radioactive source, and you'll find that the tracks of the particle from the radioactive source form condensation trail in the saturated vapor of, say, the alcohol. That's exactly the same as you see by sunset when you look at the sky and you see the condensation trails of airplanes up in the sky. So what happens is that the products of the combustion of the kerosene that planes are fueled with condenses in the saturated cold air in the upper atmosphere and create condensation trails. Now that cloud chamber adds to that condensation kind of chamber, if you want to call it initially, a magnetic field. So there is now a magnetic field that is perpendicular to the page. And when we deal later on with the Lorentz equation or the Joule equation, it's the same thing, you'll find that charged particles behave differently in a magnetic field. You'll find that charged particles in a magnetic field rotate around the magnetic field line. So if you have magnetic field lines perpendicular to the page, you'll find that the negative particles rotate in this direction, counterclockwise maybe, and the charged particles go in the opposite direction, clockwise. And that picture shows us here the fact that electromagnetic radiation, as we said here, and mass are equivalent to each other. Mass here is equivalent to electromagnetic radiation. You not see that equation in any textbook, but it is very simple and very obvious, and presenting it here with a proof for it. So what's happening there in the cloud chamber is that a gamma photon that does not generate a condensation trail comes in here in the vicinity of a nucleus of the gas, the alcohol, and splits itself into two particles that now have condensation trails. And one of them goes in this direction and the other one goes in the opposite direction. And they have the same radius of a circle. And the interpretation here is that the electromagnetic radiation having enough energy to turn itself into a mass. And this is a process that happens to gamma radiation. So the radiation source here is emitting gamma radiation, and one gamma photon that had an energy of higher than 2 electron masses has generated a positive electron moving in this direction maybe, and a negative electron moving in the opposite direction. So electromagnetic radiation has turned into a mass once it exceeded enough energy to create the mass. And that could be very interesting because we learn later about the dark energy and dark mass of our universe. And that could be an explanation, is that that dark energy and dark mass is electromagnetic radiation that doesn't have enough frequency or energy to turn itself into a mass. All right, so let's stay here. This is a proof in the laboratory that electromagnetic radiation can turn into mass. This is what we call the pair production process. The pair here is an electron and a positron, and electrons and positrons are matter and antimatter. Our universe on Earth here, part of it is a universe where electrons exist. So it's an electrons kind of a universe. If the antimatter of the electron is generated like here, it finds itself an electron and annihilate and turns into back again into two photons. One of them would be half the energy of the positron, in that case, the antimatter of the electron. And in that case, the electromagnetic radiation deteriorates into lower energy electromagnetic radiation. It may be that there are other universes, the cosmologists kind of speculate, that would be mostly antimatter or the positron-based universe. But we live in the universe where electrons predominate and antimatter, the positrons, are very, very short-lived. Nevertheless, the positron emissions from certain isotopes like fluorine 16 are used in nuclear medicine, for instance, in what's called positron emission tomography. We can monitor or measure biological processes by using the positrons that are generated from isotopes. They are very short-lived, but we use them in PET scanning, PET, positron emission tomography scanning in general. Having written those two expressions where energy mass is equivalent to electromagnetic radiation, we can venture a little bit more and deduce an interesting equation of nature. We can say that mass then is related to the frequency of radiation by a constant of nature that is really the Planck's constant divided into c squared. And it would be a very, very, very small number because Planck's constant 10 to minus 27 here, and c squared is, that's at 3, 10 to the 10th the speed of light squared. It's a very small quantity constant here. We call it the R constant. How maybe it's, nobody has basically reached that relationship before. And if you take it in the conventional system of units, the R number is minus 10 to minus 48. And if you take it in the SI, or the Système International system of units, so in that case, the Planck's constant is joule second, and the speed of light is meter squared by second meter per second is the speed, that's c square meter per square per second square. You find it's an equally small number, 10 to the minus 51 joules second cube per meter squared. Now, having said that, that mass delta M is equivalent to delta E, then we take the 1 gram of matter. We said on 1 gram of matter here multiplied by the speed square of the speed of light. This is the relationship, famous Einstein equation. You'll find that basically 1 gram of matter is equivalent to not such a small quantity like we have derived here, 10 to the minus 51, but such a huge quantity. 1 gram of matter, if totally converted into energy, can produce for us here a large, very large amount of energy, 10 to the 13th, 10 joules. And if remember that we calculated here in ergs, but 1 erg is 10 to the minus 7 joule, or 1 joule is 10 million ergs, 10 to the 7th erg, you'll find that 1 gram of matter, if totally turned into energy, produces a tremendous amount of energy. That's 10 trillion, 8.9 multiplied into 10 trillion joules of energy. Now we know that the mass of the electron is 9.1 10 to minus 28 gram. So if we substitute instead of the 1 gram here, and we have an electron that totally converts itself into energy, so you substitute the mass of the electron, 10 to minus 828 grams, multiplied by the square of the speed of light, and you'll find that each electron in mass units, its mass is equivalent to 0.51 million electron volt. And the electron volt basically is the kinetic energy acquired by an electron if it is moved through a potential drop of 1 volt. And in that case, you find that we can redefine the atomic mass unit as that 1.6 10 to the minus 24 gram, which is equal to the mass of the electron multiplied by 0.51 million electron volts per electron, and divide by the mass in grams of a single electron. And we get something very interesting now. We can get these atomic mass units in terms of electrons cancels with electrons, gram cancels with gram, in terms of million electron volt. And what we get today as a result here is that 1 atomic mass unit is equivalent to 931, let's say 0.5, 931 million electron volt. That's approximately 1,000 million electron volt of energy. I'm going to jump and then come back to that section later on, and go now to our nuclear reactions that we tried to quantify, and start calculating how much energy is produced from our nuclear reactions based on that difference in the masses. And in that case, we take binary reactions, binary in the sense that A plus B reactants produce for me C plus D. And we will find an example as we go along. However, if I want to balance the mass and energy on the two sides of the nuclear reaction, I have to consider not just the rest mass energies of the reactants, but also their kinetic energies. They're moving. They have kinetic energy as well as their mass. So if you are moving yourself, when you move or run, you have your kinetic energy as running, but also your mass itself is a form of energy. So the kinetic energy of the plus the rest mass energy of the reactants should be equal to the kinetic energy plus the rest mass of the products. And that balance has to occur because nature likes to balance itself out. Let's turn this description here, equation 29, into a mathematical form. So the kinetic energy will be written as E sub A, and the rest mass energy as mc squared for the reactance A. And then I have the kinetic energy plus the rest mass energy of the reactant B. That should be equal to the kinetic energy plus the rest mass energy of C plus the kinetic energy plus the rest mass energy of D. Now remember that nuclear reactions have a change in mass. And if we take the mass of the reactants, which is the rest mass of the reaction as m sub AC squared plus m sub BC squared, and subtract from it the mass of the product, that's m sub DC squared plus md sub c squared, we can determine how much energy is released from the reaction. And we call that energy release the Q value of the reaction. Notice here that we are calculating it in terms of the masses of the reactants minus the masses of the products, which is what we can calculate because we know what are those elements by balancing the nuclear reactions. And from this balance equation, you'll find that the difference between the masses of the reactants minus the masses of the products has to be equal to the kinetic energy here of the products C and D minus the kinetic energies of the initial reactants A plus B. It is very obvious that I can calculate that quantity by knowing the masses of the products and the reactants from the chart of the nuclides rather than taking each one of the reactants and calculating its speed or measuring its speed. We cannot do that, but we have access to the masses, so we can calculate how much energy is produced from a nuclear reaction. You'll find this is obviously because it's easier to access the masses of the nuclei undergoing nuclear reactions than it is to go and calculate the speed of each reactor. It's just impossible here in general. You'll find that because of this, you'll find that the energy releases from nuclear reactions do not consider the kinetic energies. Instead, they consider calculating the V value by the difference in the masses between the reactants and the products. We have a problem though in the periodic table of the elements. When we talk about nuclear reactions here, we are talking about masses of the nuclei. These are reactions between the nuclei. But when we go to the chart of the nuclides, you'll find that they list the masses for us for the neutral atoms, because that's what we get from mass spectroscopy. So what is the neutral atom? The neutral atom is the mass of the nuclei plus the mass of the electrons. So, however, you'll find because of the conservation of charge, the charge on A plus the charge on B should be equal to the charge on C plus the charge on D, which is the total number of electrons here and the total number of electrons here. So if you multiply each isotope by its number of electrons, then the Q value, in fact, if I use values from the periodic, from the chart of the nuclides, it is, you'll find that the masses of the electrons in A plus the masses of the electrons in B cancel out with the masses of the electrons in C and the electrons in D. So in that case, this is the mass of the neutral atom, and that's a mass, remember, that we get from the chart of the nuclides. All that theory here in equation writing can be simplified by looking at an example. When we dealt with thermonuclear reactions in the last lecture, we talked about their fusion reactions using the reaction between the two isotopes of hydrogen, deuterium and tritium. Deuterium is a form of hydrogen that has an extra neutron. So you find that it is still hydrogen because it has an atomic number of 1, but it's a heavy isotope of hydrogen. So that's a heavy hydrogen, if you want to call it. And still a heavier isotope of hydrogen is tritium, where we have now 2 neutrons and 1 proton. So if you have 1 proton here and 2 neutrons, the mass number is 3. It is not actually 3, it's 3.016049. But we know that when we balance the two equations, when we fuse in a thermonuclear reaction or in the future in a fusion reactor, deuterium plus tritium, the two isotopes of hydrogen. That's why, by the way, hydrogen bombs or thermonuclear weapons are called hydrogen bombs, because they use isotopes of hydrogen deuterium and hydrogen as tritium. You'll find that when they fuse together, they form a compound nucleus, and that compound nucleus splits into a neutron and an alpha particle. So in that case, we try to imitate really on Earth here what happens in the stars. In the stars, it's hydrogen per se that fuses with other nuclei of hydrogen, still producing alpha particles, and of course, solar radiation or the radiation from stars is propagated in the rest of the universe. Now, for that DT reaction that happens in thermonuclear weapons, or that we are trying, in fact, to master it for controlled fusion reactions, we would like to estimate how much energy comes from that reaction. So we seek the chart of the nuclides. We go to the chart of the nuclides. We get the mass of deuterium, it's 2.014102 atomic mass unit. The mass of tritium, the mass of a neutron, and the mass of the alpha particle. And the Q value is going to be the difference between those masses. The mass of deuterium here, the mass of tritium here, the mass of the neutron here, and the mass of the alpha particle here, and subtract those masses from each other, you find that there is a difference in mass of 0.018882 atomic mass units. And we have established a few minutes ago that one atomic unit in mass is equivalent to 931.481, or let's say 931.5 million electron volts per atomic mass unit. So in that case, the mass in atomic mass units here cancels with the equivalence of mass to energy, million electron volts per atomic mass unit, and we get 17.6 million electron volts from that particular fusion reaction, deuterium plus tritium. And that is the basis of the energy release from thermonuclear weapons and the energy release from our future first generation, probably, because we know about that reaction fully, our first fusion reactors that people, both engineers and scientists, and are working on. So this establishes basically that we can balance nuclear reactions. Let me move further and ask a question, like if that reaction produces 17.6 million electron volt, first, how does it compare to fission? A fission reaction, we know from the earlier lectures or chapters, produces about 180 million electron volt per fission reaction. So in that case, you find that a fission reaction, 200 million electron volts is basically 10 times, about 10 times the energy released from a fusion reaction. All right, now another question comes out is how, if we release here in that reaction 17.6 million electron volt, how does that energy apportion itself between the neutron and the alpha particle? In that case, the conservation of charge, 1 + 1 is equal to 0 + 2, and the conservation of nucleons, 2 + 3 is equal to 1 + 4, has to be supplemented. We supplemented it already here to estimate the energy by the conservation of mass / energy. We need to complement it from mechanics, the laws of mechanics, with the conservation of momentum. We are going to say that the momentum of the deuteron plus the triton should be equal also to the momentum of the products, the neutron plus the alpha particle. So in that case, we will be able to apportion that 17.6, how much goes to the neutron and how much goes to the alpha particle. So jump ahead here and try to apply the conservation of momentum, or in fact, the section on the energy partitioning in nuclear reactions. To make things simpler, and not to worry about the angles at which the products are emanating from the reaction. We assume that the reactants and the products fused together and that they were initially at rest. So you'll find that the results do not differ from what we get if we assume that they had initial kinetic energy. So if the two reactants are combined together into a compound nucleus, it splits apart because that compound nucleus have now too much energy. It behaves like a liquid drop that wiggles around. The two parts of the in the wiggling of this is called, in fact, the liquid drop model of the fusion of nuclei. You'll find that the electrostatic repulsion repels them away from each other, and the momentum of one particle by conservation of momentum should be equal to the momentum of the other particle in the products. You see here, I'm saying that the reactants A and the reactant B have initially zero energies, that are at rest. So now the two products C and D have momentum that moves in opposite direction, and their momentum should be equal. Let's manipulate that equation a little bit just for the fun of it. Let's square it. So in that case, m sub c squared should be plus v sub c squared should be equal to m sub d squared v sub d squared. Let's separate one of those m's here out from each one of them. I have an m sub c out here and m sub d out there. Let's multiply both sides by 1/2. So we get here 1/2 m sub c v c squared, and this is 1/2 m sub d v d squared. You immediately recognize that half mv squared for c is the kinetic energy of c, and the half m sub d v d squared is the kinetic energy of d. So we can rewrite those equations now relating the mass of the product C and its kinetic energy and the mass of D and its kinetic energy. Now this is a description of how momentum is conserved in that case. However, we also have conservation of energy. The conservation of energy was described a few moments later as the kinetic energy of the product C plus D minus the kinetic energy of the reactants. But we assume that the reaction is the initial reactants were at rest. So the two other terms here disappear, and I can relate the kinetic energy of the product C to the Q value of the reaction and the kinetic energy of the other product E sub D. So now we have two equations. One, the conservation of energy here in a different form, and the conservation of momentum in the previous equation. Now we can eliminate one of the two kinetic energies. So let us eliminate the kinetic energy E sub C here in the conservation of momentum equation, and we end up in the two in the equation of conservation of momentum now, with the Q value appearing, the kinetic energy of D appearing, and we can basically calculate the E sub D here as the mass of C multiplied into the Q value and divided into the mass of both the product of the reaction. And by substitution, because E sub C is equal to Q minus ED, we can also calculate the kinetic energy of C in terms of the Q value. Now there's something very interesting here. You would think that the kinetic energy would go for D would go depending on the mass of D. Not so. You see here that would go against our intuition. The kinetic energy of the products of the reaction distributes itself in inverse proportion to the masses of the particles. So the kinetic energy of D is proportional to the kinetic energy of the other product, M sub C, and the kinetic energy of C is proportional to the other kinetic energy of M sub D. So the mathematics here and the physics go against our intuition. You would think, oh, the heavy particle carries more kinetic energy. No, the lighter particle carries the kinetic energy. So in that case, using that equation, you'll find that the energy of the neutron is going to be the mass of the alpha particle, the other particle, divided into 4 plus 1, the mass of the alpha particle plus the neutron. I'm using an abbreviation here, multiplied into 17.6. So the neutron, the lighter particle, is going to carry 14 million electron volts of energy, and the helium nucleus is going to carry the least amount of energy. But both of them add up, obviously, to that 17.6 energy released from a fusion reaction. Notice here something interesting now, comparing fusion to fission. We said that fission has a much higher energy release, 200 million electron volt, than fusion, which is 17.6 if we take the DT reaction as an example. However, look at the energy of the neutron from fusion, 14 million electron volts, whereas the energy from fusion, from fission, is only 2 million electron volts. So we can conclude here that fusion is energy poor, but neutron rich. It's very high energy in the neutrons, but it only produces 20 million electron volts. And on the opposite side, fusion is energy rich. It produces 200 million electron volts of energy, or to be exact, 180 million electron volts, but its neutron is poor. It produces only a neutron with 2 million electron volts of energy. And that combination between two basically components that have different energies and different kinetic energy of their components allows us to create an optimal combination of the two. And this is a case that we call now a hybrid. So in our future, we may have a nuclear reactor that uses both fission and fusion. In fact, a thermonuclear weapon, if you remember our second chapter, uses a multi-stage amplifier. We start with fission. Fission produces X-rays and neutrons. The neutrons turn the lithium in the lithium deuteride into tritium. The tritium and the deuterium fuse together. And then very energetic neutrons now are generated, 14 million electron volts. So they surround the casing of the device with uranium-238, and that can lead to the generation of more fission energy. So it's a fission, fusion, fission process that would be the hybrid, and that happens in nuclear weapons, and we would like in the future to apply it to basically a controlled fusion reaction. We have to really also very quickly look at the fission process. The fission process is not a binary reaction. A neutron hits a uranium-235 nucleus. It splits it into those two fission products that have like krypton-97. It's not kryptonite, it's krypton-97 and barium-137. And in the process, 2 to 3 neutrons are emitted. So the Q value is going to be the mass of the neutron plus the mass of the nucleus of uranium-235 minus the mass of the krypton-97 plus the mass of 197 plus the mass of 2 neutrons. In a chain reaction, 3 neutrons or 2 neutrons are produced. We are showing 2 to 3 neutrons here. One of them escapes from the reactor surface. One is lost through radiation. And we designed the system to have only 1 neutron surviving per generation, causing the fission in another nucleus. And we allow 1 to escape, 1 to be absorbed, and another one to cause another fission, and so on. And this is what we would call a nuclear chain reaction. If you calculate the value of the, it's not a binary reaction, but to calculate the Q value of the fission reaction that we have put together in the previous chapters, you find that if you go to the chart of the nuclide, the mass of a neutron in atomic mass units is here, the 235, the krypton, the barium, and in that case, you can calculate the Q value of a fission reaction, mass of neutron plus 235 minus the mass of krypton-97 minus the mass of 137 minus the masses of 2 neutrons. You get a very small amount. Remember, you have to go to several decimal digits so that you don't lose resolution. It's a difference in mass of 0.2 atomic mass units in a fission reaction. convert that to using our conversion factor 931, and here it is, 193 million electron volt. We said that's about 200 million electron volt, and when we allowed for the escape of the neutrinos, we said it's 180 million electron volt. So fission produces, say, 190 million electron volt per event, or 200 or 180, but fusion, as I suggested a few minutes ago, produces only 17.6